Right, so the plan for the second half is, we can't just beat around the bush. I want to actually go into a proof of a proper lifting theorem. So the aim is to kind of sketch some key ideas for this theorem, deterministic lifting, which I formulated here exactly as it's been proven by Ross and Mackenzie. I'll still sketch a proof, not their original proof, but using more modern notions. I don't know why, I just want to maybe entertain myself here. So the proof sketch is in two parts. It's a kind of first a bottom-up approach and then top-down. So I'll start with very low-level details about we want to try to formalize in what sense do these gadgets fool communication protocols, or really rectangles, which these protocols are comprised of. So it's we try to make formal the sense in which a protocol can't predict the outputs of the gadgets if it hasn't communicated enough information. And so then with these lemmas in place, we can start arranging them in an argument that would actually prove such a theorem. So really the focus is on, of course, the hard direction, which is why do we get a lower bound on communication? Okay, so I should mention, if you haven't seen communication complexity before, how do you analyze a protocol? So it's all about rectangles. So if you have a communication problem, again, I view it through its communication matrix, Alice's inputs, Bob's inputs. You can visualize a deterministic protocol, as we saw previously, as a tree, but also kind of visually as doing something to this communication matrix. So if Alice sends the first bit, I visualize it as splitting the communication matrix along rows into two parts. So those rows, those inputs to Alice, where Alice sends a 1, those rows where Alice sends a 0. It's the first bit of the protocol done. Now Bob speaks. I view Bob sending of a bit as further refining this partition of the communication matrix into rectangles. So maybe here Bob sends a bit, sends a 0 here, 1 here. And I mean, again, Bob's message is a function of the bits that came before. So the partition in the lower half of the matrix could be different. So this goes on for some number of steps until the protocol finishes and we are at the leaves. So that gives just a labeling for all of the leaf rectangles. And we have now supposedly computed the Boolean function. So the Boolean function should be monochromatic on each of these leaf rectangles. So really, to analyze communication protocols, we just need to start at least to analyze individual rectangles in the communication matrix. So I'll start with just formalizing what it means for a single gadget to fool a rectangle. So it's a sense in which a large rectangle cannot predict the output of a particular gadget. And this is classical stuff, by the way, from the 80s. So those who are in the know, we've chosen our gadgets to be good two-source extractors. That's one way of putting it, but you can ignore this terminology. I'll just develop it from scratch. So let me, for this gadget part, let me actually use a smaller gadget than indexing because I find it's easier to develop it for the inner product gadget on B bits. So we'll switch to indexing later on, but somehow I like to work with this for these initial lemmas. Okay, so here's a sense in which the inner product fools rectangles. So this is the kind of single gadget lemma. So suppose I have a large rectangle in the communication matrix. So I have sets X and Y. Okay, so both are subsets of B-bit strings. And suppose they're large. I want to argue that they're large enough rectangle has a hard time agreeing with or being monochromatic. So if this is the communication matrix of inner product, let me make an observation first. The matrix does have relatively large, moderately large monochromatic rectangles. So this is the inner product B. So it's 2 to the B times 2 to the B matrix. And there truly are somewhat large monochromatic rectangles of size 2 to the B over 2 times 2 to the B over 2. So what are such rectangles? Well, they're such where the rows for Alice are B-bit strings that, let's say, on the first half, they're all zeros, but the remaining bits are unrestricted. So this is a set of strings of size this much. And if I take these as rows, I can take as columns like an orthogonal space. So unrestricted on the first bits, but 0 on the second. So clearly, every vector from here and here, they're orthogonal. Their inner product is 0. I've identified a relatively large monochromatic rectangle. What this lemma says is that if you pick sets that are even slightly larger than this, then it no longer happens. Then every such rectangle is roughly balanced. Okay, so I should credit this to Chor and Goldreich, who basically introduced, I think, two-source extractors, and this is one of their lemmas, arguing that inner product is a relatively good two-source extractor. So I want to say that there are roughly equal number of zeros and ones in such a rectangle. So the claim is that if I pick little x from x uniformly at random and little y from capital Y uniformly at random, maybe I use this for picking at random, then let me use the plus minus 1 basis. So even though inner product is a 0, 1 matrix, let me just quickly switch to plus or minus 1 notation. So the inner product of this little x with y, mod 2, but I can omit it because it doesn't really matter for this expression. So this is just counting kind of the disparity of yes and no inputs inside this rectangle. So I claim this is small. The absolute value of this is exponentially small. So, okay, I should qualify. Let's say the size is here. Oops. Okay, so they're slightly larger than this example of monochromatic. So 0.6b. With such large rectangles, you do get this exponentially small bias. Okay, large rectangles can't predict the output of the gadget. And the proof of this is actually very short. Wonder how intuitive it is. It's not very intuitive to me because it uses linear algebra. I'm more of a combinatorial person, but let me still give the proof of this. So let me call this 0, let's say the plus minus version of this matrix, the H matrix, for a Hadamard matrix, because that's what it is. So let me write this as trying to count in linear algebraic terms the number of ones and minus ones inside a given rectangle. I can write it as a bilinear form. So if I take an indicator vector for x, I guess transpose, and this plus minus 1 Hadamard matrix. So this is simply an expression that counts the disparity of plus and minuses. And I need to normalize, because this was really an expectation or an average. So I'll normalize by the sizes of these two things. Well, I can upper bound this quantity by just the Euclidean norm of these vectors times the operator norm or spectral norm of this matrix in the middle. So this is upper bounded by the 2 norm of this vector times this spectral norm. Okay, so this is easy. It's just the root of the size of x. Similarly here. So what's the spectral norm of a plus minus 1 Hadamard matrix? So it's a symmetric matrix, and any 2 distinct columns are orthogonal to each other. So in particular, if you compute the square of the matrix, you just get, on the off diagonal, you get zeros. But on the diagonal, it's a vector inner product with itself. So for plus minus 1 vectors, you just get the number of entries, which is 2 to the b. So this is just a scaled version of the identity, which shows very reminiscent of the calculations in the sensitivity breakthrough again. Just wanted to be on the hype train again. So you get a bound on the spectral norm, which is just the root of this. Okay, so you just plug that in. And I'm not going to do it, but we have plain numbers here now. So you plug them in, you get exactly the claimed bound. Okay, it's at least a short proof. So this is pretty fun. We can kind of understand how the outputs of a single gadget under 2 inputs that are kind of, well, they're rectangles, so independent pairs of random variables, you could say. Let me make a slight generalization of this. We won't quite be able to work with sets, but we'll work with random variables. Slight generalization. So, and this is very familiar for people who know two-source extractors, which is you can have this result even if x and y are random variables of a given high enough mean entropy. So let me define this notion. Maybe here. So the mean entropy of a random variable. So I'll kind of now switch from capital X being a set to it being a random variable. If it was a set, the corresponding random variable is, of course, uniform on that set. But now it's a random variable. And the mean entropy is some stronger notion of entropy than the usual Shannon entropy that we know of. You minimize over all the outcomes of this random variable of the log of the reciprocal of the probability of getting that outcome. Okay, so I think this is the same as saying, if I kind of move the optimization inside, it's the log of 1 over the maximum over outcomes of the probability of getting that outcome. So you can think of, if you have a random variable, x, you can have maybe outcomes here, and they're log 1 over probabilities here. So any random variable gives you some kind of a graph. And the usual Shannon entropy is kind of measuring what is the average height of these log 1 over probabilities, some weighted average of them. And mean entropy, though, it's a stronger condition of having large mean entropy. It says that you can have a uniform bound on this, that any outcome of the random variable happens with low probability. So all of this is just a slightly more general language of talking about distributions that are uniform on a set, like we were studying here. So the basic fact, like a defining fact here, is that if you have a random variable with mean entropy at least k, then that's the same as saying that x is a mixture or a convex combination of, well, these wonderful random variables that are uniform on a set. Okay, of sets of size 2 to the k. Distributions uniform over a set, these are also sometimes called flat distributions for short. So, okay, I proved a claim about flat distributions, but of course you get an analogous claim even if x and y were just convex combinations of flat distributions. So I can modify the statement a little bit to make it more general. Okay, so these guys are now random variables distributed in this domain, and they have good mean entropy. Okay, so mean entropy more than half B. And so I made this generalization because, yes, when you study communication protocols and what rectangles can do, rectangle is just a pair of two flat distributions, you can think. So why do I need to speak about this slightly more setting? Well, it's because when I have n gadgets, so that's the next step. Is to have, I want kind of an analogous statement now for n parallel gadgets. So again, I want to find some sufficient condition for random variables now distributed in the domain of the n gadgets. So B bits per gadget, but there are now n of them. And of course, there can be arbitrary correlations between the inputs to different gadgets. It's not like they're product distributions or anything like that. I want to find a sufficient condition for these random variables so that they would, when you feed them to the n gadget, they would output all possible n-bit strings as output. So this right sufficient condition we'll develop, we call it blockwise density. I'll define it in a moment, but let me just kind of write the lemma we want, and then we work backwards to find the right definition. Okay, which are, okay, so then this is our magical notion, 0.6 dense, or 0.6 blockwise dense, which I'm going to define in a moment. Then I kind of get a similar conclusion, but now for n gadgets. So now if I take these guys and I plug them to n copies of my inner product gadget, so I guess this just means that you have an output vector. So the first gadget takes the first b bits. Okay, in gadgets. That I want the output, which is a random variable, to be, well, in a perfect world, it would be completely uniform. But we can't quite prove such too good to be true statement. So I would just want this output to be multiplicatively uniform. Okay, so this means that, so if the output is capital Z, then the probability of getting any one n-bit string, well, in a uniform distribution, this would be 2 to the minus n, but now we allow some slack, so some multiplicative slack. Let's say like this, and this should hold for every outcome. So this is a good formalization for this rectangle not to have any good knowledge about the outputs of the gadget. It's as if the protocol hasn't queried them yet. But okay, so what is the sufficient condition? I mean, certainly if I want this multiplicative uniform output, it must be that each of the individual gadgets output very unbiased bits. I mean, I would ideally apply this lemma. So let's spell out what this means. So this is the key definition. And I should say, these multi-gadget lemmas, they're already specific, or they arose in the study of Lichting theorem. So this is kind of new, not extending these old two-source extractor lemmas to hold for multiple gadgets. So I say that a random variable, okay, so let's just say explicitly it's in the domain of the n gadgets. So I say it is delta dense. Okay, so if you want these individual output bits to be uniform, I mean, I would at least require that the random variable satisfy this condition. So it makes sense to require that for every coordinate, the min entropy of the ith coordinate. So this was a distribution over n gadgets, but now I marginalize it to the ith coordinate. And so this is the reason we use this notion of mean entropy rather than like flat distribution. Even if x was flat and I marginalize it, it may no longer be flat. But we can still talk about its mean entropy. We can still think of it as a mixture of flat distributions. So certainly we want there to be a lot of entropy in every block. So the maximum possible entropy is B, but let's say we have at least delta fraction of it. So if I'm 0.6 dense for both x and y, then I exactly meet the hypothesis of this lemma. Okay? So under this definition, at least, we're not done, but at least I know that just the lemma implies the individual output bits are roughly unbiased. Although it doesn't require uniformity. I didn't say anything about how the output bits are correlated with one another. So under this definition, it could still be the case that the output of the gadget is just all ones half the time, all zeros half the time. So the definition is not finished. We need to somehow give a stronger hypothesis that prevents there from being correlations between output bits. And the magical definition that works is to require not just the individual blocks have some min entropy rate, but rather for any subset of blocks, you have this min entropy rate. That turns out to work. So I'm saying for any blocks of coordinates. So there are roughly 2 to the n different choices of these blocks. If I look at the marginal distribution on that subset of blocks, I still get min entropy rate delta. So delta times what's the maximum entropy there? B times the number of blocks I'm considering. This is the definition. So a source is delta dense if for any subset of blocks I see large min entropy rate. So this definition makes this lemma true. And the proof, again, not terribly difficult. It's in some ways a clever reduction to this single gadget case. So let's see the proof. Proof of this lemma. Okay, so yes, let me denote this output by capital Z. And so now I make this gambit. I'm going to study this output distribution Z in the Fourier basis. So I'm actually going to prove a condition on its Fourier coefficients that implies this multiplicative uniformity. And the condition is, so it suffices to prove, turns out, to show that the Fourier coefficients of the distribution, so there's one coefficient for any subset of output bits. And well, what is the Fourier coefficient? It is the correlation of that distribution with parity on those bits. So it's the actually using the plus minus 1 basis here again. So if I look at the parity of the output bits on some subset, I want the parity to be roughly unbalanced, or very unbalanced, in fact. So this is the ith Fourier coefficient, and I'm shooting to prove that actually the L1 norm of them, or the absolute value of all of the coefficients, is so small that if I sum everything together, I still get a small value. So the sufficient condition for multiplicative uniformity is if I sum over all subsets that are non-empty. This expression is, well, small, subconstant, let's say. So it's a very basic Fourier calculation, which it's a one-liner, but I won't show it, that a condition like this implies this multiplicative uniformity. So this is an interesting fact, I suppose, in your own work. If you ever want to prove multiplicative uniformity, you can do it by looking at the Fourier coefficients. In my limited experience, I don't know of any other way, I have very limited experience, to prove a claim like this in any other way. So yeah, at least in the lifting literature, whenever you're shooting for this, you switch to this Fourier perspective. So I want this sum to be 0. I want to bound these correlations with parity. And concrete numbers that suffice is if I can bound each term that is exponentially small in the size of I. So if this would be exponentially small in the size of I. So it takes some work to see that, I mean, it's, again, a silly calculation, that if I can really prove this bound, then the sum over everything is small. Here, crucially, and this is the only point in the proof where I need to assume a large gadget. So I need to assume, you know, for this silly union bound to work, that B is at least log n. Only place in the proof, I think, where we need a large gadget. And that's already because, suppose I just want to bound the level 1 coefficients. So when this I is a singleton, okay, I have n terms. If I want them to sum to something small, the biases need to be smaller than 1 over n. The only way I can do that is to have B be logarithmic. And in fact, the level 1 Fourier coefficients, I can bound them using this lemma. It's exactly the claim. This bound is this bound. But what remains to show is, well, how do I bound coefficients with a larger I? It's also a reduction there, but it's a bit clever. So here's the reduction. This is, I want to show this for every non-empty coefficient. So I need to bound this parity. Well, what is it? So parity of these output bits. Okay, what is it? It is parity of some inner product gadgets. Okay, so this is the subset of bits I care about. These gadgets, these output bits, and I'm interested in their parity. How can I bound the kind of the output balance of such a function? Well, the key observation is this is nothing but a larger inner product function. XOR of inner products. Inner product itself is an XOR of ANDs. So this is just a larger inner product. Inner product on B times size of I bits. And the inputs are X projected to these blocks. Okay, but now very conveniently, it's almost like you make this definition by seeing the proof. This is exactly the place where to bound the output bias, we need mean entropy for these two guys to be this 0.6. So now I just apply this lemma for this large, it's no longer a single gadget, but it's a larger inner product function embedded in this domain. Okay, and that's the proof sketch. I mean, I omitted this one line Fourier calculation that this really suffices, but I don't think it's terribly illuminating. So this really concludes this formalization of why these gadgets fool large rectangles. We have nice, clean, sufficient conditions for the gadget outputs to be close to uniform. And now we can forget all about Fourier analysis. We just, in fact, I would just like to start erasing stuff. We just use this as a black box. This is the only kind of key lemma that we need to prove this lifting theorem at the end. Okay, so these lemmas were very slick to prove for the inner product gadget because of this very final step. But now I'll make this weird move of switching the gadget because the rest of the proof is easier for another gadget. So I hope you'll allow me that. Okay, so let me just record the analog of this for not inner product but indexing, which we'll actually use. Okay, so indexing, it embeds inner product, but it's a larger gadget, so you might hope that it's easier to work with it. And indeed, we get this lemma with less constraints on the inputs, which is it's nicer to work with because of that. So I now switch to this indexing, and let me choose the this M, this how many values of pointers Alice has as polynomial in n to 100, let's say. So then the inputs to this indexing are, or n copies of indexing. Alice gets a pointer for each of the n coordinates. And now the hypothesis is, again, for this variable, that this is dense, 0.6 dense. But what we gain from looking at indexing is that for the other player, the one with these really long bit strings, we can assume much less, which is just that the set or the entropy is rather large. So the hypothesis is that y, so this is of the form m bit string for each of the n gadgets. And I'm just requiring something like this, that it has a relatively large mean entropy. So the maximum possible would be m times n, but I can allow some slack like this. And let me just say why this is such a weak condition. In a communication protocol, the rectangles we encounter after roughly k bits have been communicated, you roughly have, as random variables, a bound which has only lacking k bits in entropy. So k bits of communicated, k bits is what you lack from having full entropy. But here, the hypothesis even allows a large polynomial loss. I mean, in a communication protocol that would ever even communicate at most n bits, this is allowing a lot. So we don't really have to worry too much about ever losing such a weak property. So that's kind of the gain. So under this hypothesis, we have the same conclusion. Okay, so I'll really use this in the proof. Okay, so here's the high level of how to put this into an actual lifting theorem. So the high level of the proof is we're given a communication protocol for this composed function, and from it we want to extract a decision tree just for the outer function. So let me maybe just write that down. Extract a decision tree from a given protocol for this composed function. And in fact, in the proof, this extraction is going to work for every f. So in some sense, f is not, there's nothing special about f. It works for any f. And in fact, in this extraction process, we don't worry about f at all. The kind of correctness of the decision tree will follow that of the protocol. But it's really about how these gadgets are obfuscating the inputs to the outer function. So the way we're going to do this is we're going to start as a decision tree. Now we've been given, as a decision tree, we've been given a query input. Okay, so it's some small z, n-bit string. And we want to take a walk in the protocol tree, starting at the top, down the protocol DAG, guided by occasional queries to this unknown input z. So the walk is going to depend on what exactly z is, and we're going to occasionally query bits of it to learn more about it. And so the main invariant we're going to maintain during this walk is going to maintain a rectangle that kind of models where we are. So when some bits are queried, the corresponding gadgets will be fixed, and the remaining will be unrestricted according to these lemmas. So I'll spell that out. This is the main invariant for this extraction or simulation. Okay, so we are at some node in the protocol tree. We're going to maintain a rectangle. So let's say it's x and y. So okay, so the picture is something like this. We have our communication matrix. And at start, we're just going to, at the root, we're going to maintain the whole rectangle, the whole domain. Then Alice sends a bit. Okay, this again causes this splitting of the communication matrix into two, so maybe like this. And our default action is to have this rectangle be maintaining. We're going to shrink it every step. So here we would choose whether we want to shrink the whole rectangle either to the left side or the right side. And by default, we're just going to do a greedy choice, always restrict to the larger side. So if this is really what's happening, I would go to the left. This would be the next rectangle I'm maintaining. So far, the rectangle I'm maintaining just matches the natural rectangle associated with the node of the protocol, which is the set of all inputs that reach that node. But the protocol itself, these natural rectangles, they're pretty arbitrary. They don't have any structure. And that's why we're going to maintain a smaller rectangle contained in the natural one that does have more structure. And the structure is this. So there's some, these properties. I call it, this is the, okay. this is the super key invariant, is there is some subset of blocks. So these represent the bits that have been queried so far. Initially, it's the empty set. And the rectangle we maintain kind of respects the queries in the sense that, firstly, the gadgets corresponding to these blocks are fixed. The inputs to these gadgets are fixed. So Alice's pointers corresponding to these blocks are fixed. So they're pointing to fixed positions in Alice's, in Bob's strings. And moreover, the bits I'm pointing to in Bob's input, they're fixed too, causing the gadget outputs to be fixed. So the indexing gadget on these I blocks, if I feed the rectangle in there, I get a fixed output which is consistent with the queries I've made so far. So I guess the basic correspondence is that in a decision tree, each node is associated with a subcube. Some coordinates are known, rest are completely unrestricted. And here we are trying to model that by a rectangle. Rectangle whose image through the gadgets is exactly a subcube. It's fixed on these blocks, coordinates, and second, completely kind of unrestricted on the other blocks. So now we say that we meet these, the hypothesis of the lemma, that x on the remaining coordinates is 0.6 dense. And also, well, the y, it comes along, it is large enough, not hard to maintain. Okay, so either project it to the free coordinates or not, doesn't really matter. So this is the basic correspondence. You've queried something that corresponds to the rectangle we're making, having the corresponding gadgets fixed. The remaining are still, unpredictable.
So in the condition 1, so you see the output of the gadgets are fixed, but not are the inputs to the gadgets fixed? Or
Right. So that is a distinction. It's not really important. I could define it both ways. This is maybe a bit more sparing. I just say that Bob's bits that are being pointed to are fixed, but the whole string may not be fixed. But
so it
doesn't really matter. So if I promise that I'm going to do this, and just kind of at every step, maybe I need to increase this, because I'm constantly shrinking this rectangle, so I might have to query more bits. But if I promise that I can somehow keep the size of this set bounded, well, in terms of the height of the protocol tree, then I hope you believe that the simulation or the lifting theorem follows. Because if I can reach a leaf, so that this is kind of, should be obvious, but I'm still trying to kind of say it out loud. You reach a leaf where the image of the rectangle you're maintaining is the same subcube as in your simulation. So as a decision tree, you should be able to output the same answer as the communication protocol. Okay. Because the communication protocol says that this is the right answer for all of these inputs in my rectangle. It follows that that answer must be, Okay, maybe I'll spell this out even though I'm saying very little. So I've reached a leaf, I've queried some bits, the remaining are still unknown. And I claim that the leaf value is the right answer for the value of this function. Well, why? Whatever the input is that I'm actually have queried, so it has some completion. So that's a full input. Well, the rectangle I'm maintaining in the leaf is going to contain some pair x and y that through the gadgets maps to, well, I have the whole subcube available, so I can certainly choose a pre-image that of this particular string. And so the function only depended on the outputs of the gadget, right? And so that you're kind of borrowing the correctness of the decision tree or deriving it from the correctness of the protocol. Okay, I don't know if that was perfectly clear, but intuitively it should make a lot of sense. So really, all I need to argue in remaining half an hour is how do I maintain the invariant round by round? Will?
Correctly. Like, so this decision tree, I mean, the only true input is Z, but it wants to somehow, simulate the communication protocol, which has, these more basic inputs X and Y. So the decision protocol, the decision tree is, it's just sort of imagining, like, it invented this X and Y so that it can simulate the communication protocol, and R is like the set of all possible X and Ys. Is that right?
Right, so one way to maybe say it is that the decision tree at every point, it just knows that its input is in a subcube. Okay, so it knows few bits, some it doesn't. And so that's why I'm maintaining a rectangle that that also has the same uncertainty about the input. The gadget outputs are exactly the same subcube. The protocol doesn't know which one of the gadget outputs is really the current input. So I'm really maintaining a family of different communication inputs.
Thanks.
More questions?
I'm having a little trouble reading conditioned. So it's one condition about X and the other is about Y. Is that?
So I should maybe rename these somehow. This is a condition about the fixed part. So I'm talking about this set of blocks I, where the gadget outputs are fixed. That's what I'm trying to say. So Alice pointers are fixed there, and so are the gadget outputs. So this condition is claiming something about Y too. And the second condition is about the rest of the coordinates, where I'm trying to say it's unpredictable. So the free coordinates. Okay, so I have exactly the conditions matching the hypothesis of this lemma. So the preconditions imply eventually that in the kind of remaining of the coordinates I'm uniform. Okay, so there's only one lemma to come that tells you how to maintain this property round by round. Okay, so I call this the round lemma. And let me again spell out what do you do in the simulation? You maintain your rectangle, one party speaks, splitting your current rectangle in half. You always go to the larger side. And so in that sense, you just lose 1 bit per round in entropy. And at some point, you're going to lose this invariant. And the way you're going to lose it is you're going to, this property is going to be violated. Actually, for technical reasons, I want to assume even larger density here. Sorry. So this is the property that actually is going to be violated at some point when I shrink and shrink my X. And so the purpose of this round lemma is to restore this property at the cost of fixing more gadgets. I guess technically speaking, you could also violate this, but again, I'm not going to bother too much with it. It's really hard to violate this condition. So we are mostly staring at what happens for these Alice's pointers, because the gadget outputs depend so much on exactly what the pointers are. So the interesting case is when I've just lost this 0.9 density for X. I'm going to formulate this lemma assuming I haven't made any queries yet, so this capital I is empty, just for simplicity of notation. So, okay. Okay, so assume I have this random variable which is not 0.9 dense, but it's just lost this property. But it's only lost its property by 1 bit. So it still is 0.8 dense. So it's kind of lost its property by only a little bit. So I want to quickly fix it, restore this 0.9 density in this lemma. And okay, so then this y variable just comes along. Don't want to bother too much with it. Okay, so now I claim I can fix this. I can increase the density by fixing more gadgets. And moreover, I can fix gadgets to any prescribed output value. Okay. So there's some subset of blocks I'm going to query. Such that no matter what values I need to fix these gadgets, I can do it. So for every assignment of bits to these outputs, there's a way to shrink my rectangle and realize these gadget outputs. So there is a subrectangle, call it x prime, y prime. Where, okay, I have restored the invariant. Okay, so the claim is this subrectangle satisfies the invariant. So satisfies the invariant with this I, okay? And, okay, moreover, in shrinking my rectangle, I don't lose a lot in the sizes of these sets. So these are some maybe a bit more technical conditions. And let me actually, this is a slight changing notation. So I care about mean entropies. Normally we have variables with n bit of entropy, but in analyzing communication protocols, we normally have variables with very large entropy, very close to n. So it's almost better to reserve notation for how much a random variable lacks entropy from the maximum possible. So let me just make this, I call it the deficiency, this small notational help. So yeah, so let's say this is a k-bit string. Then its maximum mean entropy is k, but I define this as k minus its mean entropy. So how many bits it's lacking from having full entropy. So I'll state the changes of entropy in terms of deficiency. And in this perspective, you can see how fixing some gadgets, I get an increase in entropy for the remaining ones. So, what is the deficiency in the free coordinates? Well, it's at most the deficiency I start with for x. And, okay, it might increase by a constant, but really crucially, so I'm fixing more gadgets, I get a decrease minus of deficiency in proportion to how many gadgets I fixed. So you could even put in this log m factor here. It's not very important, but crucially, a decrease in deficiency proportional to the number of gadgets I fixed. Okay, then there's a similar condition for y. Again, not super crucial, but for completeness, let me spell it out. So its deficiency doesn't increase by too much in this process. Okay, so that's the full statement of the lemma, and I just have 10 minutes to kind of intuitively argue why you can do this, or why would you expect this to hold. Let me first say is, like these conditions on deficiency, they bound how many queries I'm going to making throughout the simulation. Because the deficiency starts in the beginning of the simulation, it's 0. I have full entropy. One round of simulation, I lose 1 bit of entropy, so that means deficiency decreases by 1. Every round it decreases by 1, and this is a kind of cleanup lemma when I apply it. So I've lost this density requirement. The deficiency increases by at most 1, 2. So the overall increase is just constant per round, except when I start fixing gadgets, I get this gain. This quantity is always non-negative. So this is already saying that you're not going to make more queries than the number of steps you've taken. In fact, it's even number of steps you've taken divided by log m. It's just an optimization to get in the final theorem statement this really tight log n term. And then maybe you believe a statement like this too. So if I fix some gadgets, I might increase the deficiency of y by, well, I need to fix gadget outputs. I need to fix 1 bit per gadget, causing just an increase in deficiency proportional to how many gadgets I fixed. And now, to end, I just want to give you a silly example illustrating what this lemma is formalizing. So it's an example. So why would you expect this to be true? So let me set n equals 2. I have 2 gadgets. Both are 1 bit. So I'm just going to look at this probability space for a 2-bit probability space. Okay, so in this actual lemma, these are actually pointers now. They're just 1 bit each. So there are 4 possible values for these jointly distributed random variables. And maybe these guys are distributed uniformly on this set. These 3 elements, 1/3, 1/3, 1/3. So maybe this has just lost density for the individual blocks. So what is the marginal on this variable? Well, this is 2/3, 1/3. It's kind of biased. So maybe this doesn't have our required mean entropy. And similarly for this, neither one of these has the required mean entropy. But I claim I can fix it, or I can restore density by fixing one of these guys. So what if I restricted this one to its most likely value, which is the upper value? So after restriction, I say x1 conditioned on always being on the upper row. The conditioned distribution, okay, it's now fixed for x, but for x2, it's completely uniform. So this is a basic principle. It's not original to lifting, and this is constantly used, is that if you know too much about some variable, fix it to its most likely value, and you can indeed increase the uncertainty in the remaining of the coordinates. So that's what this lemma is doing in a slightly more fancier fashion. Okay, so I don't want to go, I don't even have time to go too much into this. So for the final 5 minutes, please, maybe you can ask questions. Liji can ask a question.
Do you believe that lifting theory was for alternate model, even including any other model?
Good question, and this was prearranged, by the way. So the question is whether, do I really expect lifting to hold for all possible models? And actually we don't. We know it doesn't. The models I mentioned, these basic randomized, non-deterministic, so forth, fine. But when you start going to classes really high up in the polynomial hierarchy, let's say Merlin-Arthur type of models, there are communication and query analogs of these, we know that these lifting statements fail. Communication protocols are fundamentally more powerful then, because these classes, they support what are called algebraizing techniques. So most famously, algebrization was used to show IP equals P space. So the analog of IP equals P space holds in communication, but it doesn't hold for query complexity. And these are really kind of fancy models of computation. But yeah, so we can't even find explicit lower bounds for their communication analogs yet. But we know that the lifting statements simply don't work, because communication protocols can do algebraizing ticks, query complexity can't do. Right, so
Could you repeat the question?
whether they are lifting theorems or unbounded error. So these would be protocols that succeed with probability just slightly better than 1/2. And such appropriately defined such communication protocols are also equivalent to signed rank. And there are some lifting theorems for these kinds of protocols, not completely satisfying ones. Not really. Sherstov had these, and I think Arkadev Chattopadhyay had these in like a decade ago. I mean, maybe they didn't use this terminology so explicitly, but like the pattern matrix method is basically lifting. Well, okay, so for number on forehead, we still have Scherstow's and other people's results that can prove lower bounds for set disjointness, for example. I mean, I guess we're struggling with just understanding the model per se. All the lower bounds we have, the strongest ones, use lifting, which is just, I don't know, some testament to, thinking this way helps. You
Just a technical question. It seems that the argument, if you look at the efficiency rate, you find divide by the number of coordinates, and you did not gain anything. Just lost it, right? So how come this?
So it's true that our rectangle is shrinking all the time. So yes, the total entropy rate and everything is going down. But this procedure is going to imbalance it. It's going to completely get rid of the entropy on some coordinates and increase it in others.
So yes, I don't see it because it seems that you gave up high coordinate, you lost just the entropy related to close coordinates. Whereas the gaining the other, I mean, on average, it doesn't seem that you gain it.
Well, I mean, this example shows you can fix one guy and gain in the other. Right, and this is proved by finding a clever restriction, which is a restriction that happens with probability that's kind of too likelier than in a random distribution. So for those kinds of restrictions, you expect a gain in the rest of the coordinates.
Should I see it from what's written on the right hand side of the code? I don't see that. I mean, why is that enough?
Come again?
Why is the condition the efficiency value of x minus I? Why does it give us?
So we want to restore density, and that condition was hidden here. I have restored density because that was part of the invariant, which is written there. Okay, Mike?
Yeah, so what is the simplest question in this line of work that people don't know the answer to?
Yeah, I'd like to know that too. I mean, I think there are... So what would be the simplest question that we don't know how to answer? There are many.
Okay, so pick one.
Okay, so let me mention my favorite problem. I don't know how much it's related to lifting. It's related to my final remark, which is to prove lower bounds for Arthur-Merlin protocols. So it's one of the weakest models of communication for which we don't have any explicit lower bounds. And the challenge is to find an explicit Boolean matrix which is not well correlated with a union of few rectangles. So unions of rectangles, it's exactly non-deterministic communication. Now I just want an average case lower bound. Give me a matrix. Inner product is a candidate, which is not correlated with few unions of few rectangles. Seems easy enough. And by the way, query analogs of this are trivial to prove. So that gives some hope. Okay.